Okay, here's a solution to your example 3 in the 1.4 notes. So determine if the equation ax equals b has a solution for every vector b in R3. And then I've got the setup laid out for you here. So in order to determine whether this thing has a solution, we can set up the augmented matrix where we have our coefficient matrix A here, which I'll copy down, augmented with our unknown vector in R3, B1, B2, B3. And so we want to find out whether this system will always have a solution. So I'll start out with -2 times row 1 plus row 2 in order to get a 0 in this position here. Okay, so that will give us, let's see, we've got B1 here. So it'll give us -2 plus 2, so that's 0. And then -2 times this, so -4 plus 1 will be -3. -2 times 0, so that's 0 plus 3. And then -2 times B1 plus B2. -2 times B1 plus B2. I'd like to also, just to keep this video from getting too long, I'll also do the operation -2 times row 1 plus row 3 in order to get a 0 in this position right here. So that'll be -2 plus 2, so that's 0. -2 times this, so -4 plus 3, so -1. -2 times this, so that's 0 plus 1. And then -2 times B1 plus B3. -2 times B1 1 plus B3. Okay. So if I want to continue to row reduce this, I think what I'll do is swap row 2 and row 3. Okay, so I'll copy that down real quick. So now this is 0, -1, 1, -2, B1 plus B3. Move this row down. Okay, and now I will do, I guess I'll do -1 times row 2. These are pretty simple row operations we're doing here. Okay, so that'll give us 0, +1, -1, and then -1 times that last entry will give us +2B1, -B3. Okay, and then leave this last row. Okay, and so now I'll do 3 times row 2, add that to row 3 to get a 0 in this position here. Okay, so that's, let's see, 0 plus 0, 3 plus -3. This will be 3 times this, so -3 plus 3, so that's 0. And then, okay, so for this last, let's do the arithmetic off to the side here. So we want 3 times row 2, which the row 2, this last position has 2B1 minus B3. And add that to what's currently in row 3, which is -2B1 plus B2. So let's see, when we combine like terms, so we'll have 6B1 here minus 2B1. So that'll be 4B1. Okay, what about our B2s? We just have the one B2 over here, so plus B2. And then for the B3s, I have minus 3B3. And that's it, right? -6B1 minus 3B3 minus 2B1. Yeah, so that's the 4. I think I might have said -6, I meant +6. So that's our 4B1 plus B2. Okay, yes, this looks good. Whoop, there we go. Okay, so determine whether this thing has a solution for every B1, B2, B3, and R3. So if we've got this expression right here, this is not necessarily going to be a consistent system. This will only be a consistent system when this expression right here is equal to 0. So the answer to the first question here is no. There's not going to be a solution for every B1, B2, B3. So we need to answer this second part. If not, find a vector B1, B2, B3 for which the matrix has no solution. So this is similar to one of the examples videos that I created in 1.3. We just have to pick any B1, B2, B3 so that this is not 0 if this system would not have a solution. So I'll go with 1, 1, 1, like I did in that previous video. That'll work for me here as well. If B1, B2, B3 are all 1, then I will have 4 plus 1 minus 3, which is not 0. Another solution for a vector B where the system is inconsistent could be something like, let's say 5, 0, 0. Because that'll give us 20 plus 0 plus 0. So that's, again, not 0. And there are infinitely many other possibilities for vectors B for which this thing does not have a